Good morning. Now we are approaching the third section of this forum. The section is about, the title is System Projects, Slab Track Projects. But I could entitle this session as particularly specific part of the slab project, of the slab track, because there are four different panels, four different speakers who speak about specific argument, specific topic of this argument. So I started with Harald Steger, which is the first, who, you can stay there or there. Yes, it's the same.
Test, test. Optimization of transition zones can significantly increase the efficiency of the railway lines. I'm Harald Steger. I'm product manager for Getzner Werkstoffe. Getzner stands for elasticity in railway superstructure. Getzner is also expert for vibration isolation for more than 50 years. We are providing our solutions worldwide, either by our own subsidiaries or by sales partners. When I was selected to be the presenter for today's session, I was looking for a cross-link between my home country and today's location in Naples. And I figured out there is a so-called wafer from a producer in Vienna. It's a cookie, and it's called Neapolitan wafer. Why is it called like this? Because the taste featuring hazelnuts are coming from the Naples area. But this is not the only cross-link between Vienna and Naples. There's a railway line counting approximately 1,400 kilometers. And if we would let travel those wafers from Vienna to Naples, these wafers would pass by approximately 883 bridges, 201 tunnels, and 1,108 turnouts. Broken cookies do not have calories. But in analogy to that, how do broken components weigh in the track? So what would happen if this wafer would transit from Vienna to Naples the rough way? This brittle wafer would completely crack. After the storytelling about wafers, let me now proceed with the technical presentation and the analogy to the transition zones in the railway track. So what are transition zones in a railway line? We consider transition zones as track areas where we have a change of a superstructure that leads suddenly to a change in the vertical track stiffness, such as transitions from an open track to a bridge or a tunnel. Another example is a transition from a ballasted track to the slab track. It could also be a transition from a regular track to a turnout area, or even within the same superstructure, like within slab tracks, there could be transition zones. Yesterday we heard that we sometimes have in the same tunnel different spacings available, and we have to choose different slabs and different mass spring systems, and even there we have to smooth out this vertical track stiffness in the track to optimize the transition zone. What are the challenges in those kind of transition zones? So you can imagine these vertical track stiffnesses somehow lead to a ramp. So each rail hits this area where you have the track stiffness, which at the end of the day increases the vertical dynamic forces over the time of the operation. So an analogy to the brittle wafers, we have also in the track components who are suffering from these dynamic loads. And how can we detect these failures in the track? There are some examples for that. So we have a transition from a ballasted track to a bridge, and what we can detect there quite often are these ballast wear detections that can be observed by white spots, and this is a sign of the ballast wear in this area. Caused by that and the ballast deterioration as a consequence of that, the high dynamic forces are increasing, and it could lead to breakages of the clips. Additionally, these dynamic forces could also lead to cracks in the sleeper, in the worst case the sleepers or the blocks in the slab track superstructure can crack. Suddenly, over the time of the operation, this track quality will decrease, and at the end of the day, the settlement could cause much more problems, also failures in the rail, and could cause rail corrugation. Now there are different kinds of approaches to solve those problems or scope those problems. The first group is what I call constructive measures. You could integrate guardrails, you could integrate a transition slab, you could reactively do a ballast bonding, or you integrate a ballast trough. Each of these solutions has, of course, as usual, advantages as well as disadvantages. I don't want to argue for or against those solutions. Guide rails, for instance, they have the advantage that they integrate additional stiffness. At the same time, it leads to higher tension in the rail seat force and to more tension in the sleeper. A transition slab somehow smoothes out the vertical track stiffness when entering from a ballasted track to a slab track. On the other hand, it's an individual solution that causes more cost. Ballast bonding leads to fixation of the ballast on one hand, but is problematic whenever you have to do maintenance work, and it's a hindrance for tamping of the ballast bed. A ballast trough prevents the ballast from flowing apart, and again, it's an individual solution that causes more cost. Since I'm a Getzner guy, of course, I have to be convinced, and I am, and I'm patient for that the alternative solution to constructive measures is the integration of elastic components. So what is this approach about? Integration of individually designed elastic components helps us to level out the track stiffnesses. Elastic components ensure that we have a better load distribution, we can elongate the bending line, and this, as a consequence, leads to minimizing of the settlements and improving the track quality, and improving the track quality over the life cycle means also we can reduce the maintenance cost on long term. Which elastic solutions do we have available? So the elastic solutions available for all kinds of railway superstructures. For ballasted track, we can integrate under ballast mats, we can integrate sleeper beds, or we can do the stiffness graduation with rail pads. For the slab track, we have available mesh spring systems, we have insertion beds for sleeper boots, or we can integrate base plate beds. When designing when you design a transition zone and you want to optimize this, there arise two questions. The first question is how to smooth out the stiffness changes, and the other one is what is the ideal length for a transition zone. And there's first of all a quite generic thumb rule. So you have to find a compromise between the technical benefit, that means the transition zone should be as long as necessary. On the other hand, you have to have a view to the cost aspect. And that means it should be as short as possible. At the end of the day, the generic thumb rule leads to the ideal length. But there are also more quantitative rules to design the optimal length of a transition zone. So the minimum length should be considered as the distance of the bogie, for instance, 10 meters. And for the right design for the transition zone, there are several rules counting a distance according to the 0.5 second rule, the 0.7 second rule, or the 1.0 second rule. What does this mean? I will bring an example on that. Imagine you have a train which is running 125 kilometers per hour, and following the 1 second rule, it means this train with this velocity covers a distance of 35 meters within this 1 second. And this brings you to the ideal length of a transition zone. When designing and optimizing transition zones by integration of elastic components, we have to find a FEM module that allows us to compute the transition zone as a whole. And therefore, it should be capable to consider different parameters. First of all, we have to have the inputs for the different superstructures. So the model should consider either you have a sleeper for the baluster track or B-blocks for the slab track, and should also be able to compute the different geometries within this transition zone. Secondly, since we are Getzner and want to integrate various elastic components, this should also be reflected in the model. Those two columns I would consider as input parameters. And the third parameters that the FEM model should be capable to calculate are the output parameters. And as I mentioned before, as we have this change in vertical track stiffness, we need to be able to calculate the rail deflection as well as the rail seat force and the sleeper tension. After the theoretical model and our approach, let me introduce you to one of our reference projects we were honored to be participating in. This first reference is located and was projected in Switzerland, in Sametan. We can see here a cross-section. The cross-section shows that on top of the tunnel, there's a development zone for adjacent buildings, and this requested vibration isolation measures. In the tunnel and in the open track, close to the development zone, it was specified a mass spring system with a natural frequency of 20 Hertz. And from the open track mass spring system, we had a transition to a baluster track, which was specified for vibration isolation in accordance to under ballast mat with natural frequency of 27 Hertz. In addition to that, this was a combination of constructive measures and elastic measures. There was integrated under the ballast mat area, there was integrated a transition slab. And the requirements for this project was to achieve a minimum difference in vertical rail deflection lower than 1 millimeter at the running train. This shows the design and the installation. We can see here the under ballast mat on the transition slab. And this panel for the transition slab had a length of 8 meters. Let's switch to the transition zone, which we call turnouts. Turnouts actually define the efficiency of a network. In terms of investment, they cause approximately 1% investment cost. At the same time, for maintenance, 25% can be related to turnouts. There's a huge number of turnouts in our network, and it's worth it to do the optimization in this area. For instance, I brought some figures from Germany. There are 78,000 turnouts in their network. Austria and Switzerland counts approximately 14,000 turnouts in today's hosting country. In Italy, we have about 37,000 turnouts installed. A turnout is a transition zone with the highest complexity. A turnout is an area with the highest discontinuity of track geometry. We can see that we have the main track and the side track. When we run over the side track, it will lead to a tilting effect. With elastic bearings, you can smooth out this tilting and smooth out the graduation of the stiffness. Here we can see a sketch of a turnout explaining again the complexity. We have in the turnout entrance, we have the standard sleepers. And when going along the turnout, we're entering the frog area. And the frog area is the most critical area. Why? Because there you have the highest complexity of discontinuity. In the frog area, at the end of the frog area, when entering the exit of the turnout, you have a transition from the longest sleeper to the shortest pier, which is the highest complexity in terms of discontinuity and also leads to the highest tilting effect. So that means the before introduced FA model needs to be further developed, reflecting the challenges that we are facing in a turnout. That means we have to be able to deal with eccentric load impact and tilting, and also we need to be capable in the model to reflect the different geometries of the placement beds in the fastening above the sleepers with the different geometries. Let's continue with one of the projects for the turnouts where we had the honor to participate, and this is the worldwide known St. Gotthard tunnel, which is the longest railway tunnel in the world so far, operated by SBB, constructed between 2009 and 2016. In total, in this tunnel, there were installed more than 400,000 elastic elements from Getzner. These were insertion beds for sleeper boots. And in this tunnel, there were also 10 slab track turnouts installed by VAE turnout systems. What was the service that Getzner provided? Together with VAE and based on the input parameters from VAE, we had the honor to do the prognosis for the rail deflection across this turnout, and we made installation plans. What were the prerequisite conditions there? The trains running there had an axle load of 25 tons for the calculation, and the speed for the design was 250 kilometers, which means the turnout is passed over within 1 second. The design goals we had to achieve: we needed to optimize the stiffness graduation in the turnout area with different kind of sleeper boot insertion beds. The transition between the LVT system and the long sleeper has to be considered and optimized, and therefore it has to be considered a static static rail deflection in the LVT system in the straight area of approximately 1.5 millimeter. And the major goal was to have a maximum difference in rail deflection along the entire switch less than 0.5 millimeter. Based on the further developed FAM model, we started design, and the solution can be seen here. We have the standard straight track with the LVT system, and this is transiting to the turnout where we have the long sleepers with insertion bed, and this is a different type compared to the straight track. In the frog area, it was a combination of two different types to smooth out the tilting and the stiffness change over there. And at the exit of the turnout, we again had the same bed as in this area. So 3 different kind of elastic beds were integrated into the sleeper boots. And for this, we calculated the rail deflection. First, for the main track. The main track consists of two rails, rail number 1 and rail number 2. Here we can see the rail deflection line for rail 1, and we can see in the critical area where there's the frog, we smoothed out the rail deflection. It's quite smooth. Same for the second rail, and then we built the average for rail 1 and rail 2. The same calculation was done for the side track, for rail number 3 and rail number 4, and the average was built. And yeah, based on this design, we generated the installation plans, and the installation was executed according to our design. I believe in the philosophy, a job is only done if it's done. What do I want to say with that? First part was done. Theoretical model was there, design was done. How to get to the second done, to have the done? We have to get an evidence that the theoretical model is verified. And therefore, the contractor engaged external authority, Technical University of Munich, to conduct tests in the prospective turnout close to the area of Erstfield in the tunnel in St. Gotthard. The measurements took place with a bunch of trains of the type ICS with an axle load of 19.8 tons. The trains were operating during the measurements with 250 kilometers in average. And there were special circumstances in the turnout for the measurement campaign. Each measuring cross-section was located under a sleeper with different lengths. One under a sleeper with 2.6 meters, 2.8 meters, and 3.0 meters. Here we can see the result. The upper graph shows the rail deflection in the transition zone entering to the turnout, and in average we had a rail deflection of 1.4 meters at the speed of 250 kilometers per hour. In the turnout area itself, specifically in the frog area, the critical area, we had an averaged rail deflection measure of 1.75. So finally, due to my philosophy, job is done because we have the evidence and we have proven that the theoretical model is the right model. I started my presentation with storytelling about wafers. Let me conclude my presentation in the same manner. So what are the benefits for the wafer if you optimize the transition zone and this wafer respectively? The railway components are protected in a smooth way. These wafers would arrive in a perfect condition in Naples. Let me summarize the benefits of optimization of transition zones. On one hand, by improvement of the track quality and protecting the components, you improve the operational reliability, you generate higher profitability. That leads to more safety and improvement of the track quality at the end of the day. Now I want to repeat a statement from yesterday from my valued colleague from Rhomberg, Sersa, Stefan von Brunn. Build and forget is not your approach. It's also not our approach. Build and forget, we completely regret. So what does it mean? You only benefit from the benefits if you are able to have the benefits in long term, which leads me to the last benefit. The improvement of the track quality needs to pay off in terms of the lifetime of our railway superstructure and needs to reduce the life cycle cost, which is able by optimizing the components, optimizing transition zones and protecting components. So the key takeaways from today's presentation is transition zones have a really high impact in our railway lines. The huge number of transition zones within a line. Remember, from Vienna to Naples, 1,400 kilometers. There were quite huge number of turnouts, more than 1,000 turnouts. We need smart solutions to cope with the challenges in transition zones. And this allows us to optimize our resources. You're warmly welcome to digest my key takeaways by grabbing one of the Neapolitan wafers on our booth. I would also appreciate your inputs and sharing your experience with me on transition zones. And for those who want to find more information, you will find a QR code on the wafers. Thank you for your attention.
Thank you, Harald, for your presentation and to tell us something about the transition zone, how to manage, how to take solutions, and thank you also to give us some data, some numbers of the work. Thank you again. The second one is Barnaby Temple, who speaks about slab track on Viaduct. So you can take this one.
Thank you very much. Do we have the clicker on here? Okay. Okay, so first comment on dress. I don't often wear a tie, so thank you very much for the organizers to match the color code. It's much appreciated. So my talk is about the Barking Riverside extension, which is a project with slab track on elevated structures predominantly, and a particular interest point was precast S&C as well, which had to solve some special challenges. A little bit about me, Barnaby Temple. I've been in the rail industry for, hesitate to say, 38 years with a variety of organizations. And I'm now working for Rhomberg Sersa. Rhomberg Sersa was introduced a little bit yesterday by Stefan, and I'm not going to say too much extra, but suffice to say that we're involved in mechanized and conventional track construction, but also specializing in slab track construction. And you see some images there of some of the mechanized plant, plus one image of the semi-automated track installation positioning system in operation in the Stuttgart project, and also track refurbishment projects. Quite a wide range of experience we have. It's worth also noting that our capability also extends beyond that, both in investigating, measuring, condition diagnosis, and involved in solution development and overseeing and supporting design processes. And these all came very much into use on this project. So my agenda for the presentation is to give a little bit of background of what the project is, where it was, just to help give context. And then I'm going to step through some key issues, a little bit about the detailed design, and then about the installation. And there's some key takeaways which I hope will be useful for you. So firstly, what is the project? Where is it? Where is Barking? Barking is in London. If you have ever visited London and been to the Shard, then this is approximately an image from Google Maps looking east from where the Shard is. So you can see the Tower of London, Tower Bridge. If you look quite a long way east, you see Barking and the River Thames winding its way. And this project extended an existing line from the station at Barking, hence the name Barking Riverside. The extension took a spur off the line to a new station near to the river. And this was to support a big development of new housing. There was a requirement for sustainable transport, and therefore an extension to what became the London Overground extension was decided for the new population. Here's a short video that shows the simulation of the project from before design and construction. So the extension takes its way up a ramp, over some railway lines and a depot, over rivers, then under some power lines, and then takes another curve around the development, schools, houses, past a power station also that's there, then through a junction and into the Riverside station. And if you're sharp, you notice that there were square windows in the precast element, so that's an indication that it's actually the poor STA system that was selected for the project. So a little bit on timeline. So our involvement actually started well before the construction in 2017, when Arcadis, who was selected by Transport for London as the designer, needed some help with what the client wanted. The client wanted slab track. They wanted precast slab track, and Arcadis didn't have that experience. So we were brought in as advisors to help, and we even took them to a site visit, courtesy of POR, in Germany to see some installations, so they got a better feel for what they were designing for, because they were designing the substructures and viaducts. Move on a year to 2018, we got involved again, this time directly for Transport for London, because Arcadis had done a track bridge interaction study. And it was important that this got reviewed, because there were some pretty critical aspects of planning for tendering and construction that we needed to know, or the client knew he needed to know, but they didn't have the expertise in-house. So we were able to support them doing the assessment of what the study had showed. And what it showed is they needed to do it again, actually, but we'll come back onto that. And then the tender for the main works civils contract was completed in 2018 with the appointment of Morgan Sindall Volker Fitzpatrick joint venture. And we were appointed as their subcontractor for design and build of the slab track. We were supported in that by VCE, who you've been introduced to already as our specialist designer. That design process went on until about mid-2020, which, if you remember the COVID timeline, did then interrupt the project program a little bit, and the construction was actually delayed. The viaducts took a little bit longer because of that, and our installation was still during some COVID measures, so there were some disturbances to the smooth running. So 2021, we were able to install the slab track, and the line was actually opened in 2022. So a little bit more about the route in detail. Firstly, I mentioned the ramp. There's the ramp. It starts just underneath the road bridge. Has to get to a certain height to go over a railway line. Then there's more railway lines. This is actually a freight depot. And then actually the high-speed 1 railway tunnels run under here. So there was a raft built to help protect that. And then this curve runs around 220-meter radius with steel girder viaduct decks, and then onto a predominantly concrete viaduct all the way through round to the station, which is there at the end. So the junction is there, the station is there. So I'm going to start this time with some thanks and acknowledgements, because one of the main themes for me for this project was you get somewhere much better in collaboration and cooperation with your subcontractors, your client, and your other parties in a job. So, you know, I have permission to do this presentation from Transport for London. Network Rail played a role. Morgan Sindall Volker Fitzpatrick were a great client. But I had some really key suppliers. CEng, Paul Inslee, wherever you are, was a great help working with CEng at the time. First Alpine, we had to use them, POR, and specifically our expert designers, Fritz Cherry and Partners, known as VCE in the international market, and Schembera Consulting, who helped with some advice and design checking as well. And my co-author, not here today, is Chris Hardwick, and without him, the paper wouldn't have got written. So thanks to him as well. So early stages, I mentioned some key issues. Well, one of the key issues was that S&C on precast, while not unknown, hadn't been done in the UK before. And we identified on the site visit that whilst it looks really nice, what we saw, but actually the switch drive, the rail fastening systems, and indeed the precast slabs, were all going to be effectively new products to the railway in the UK. So not so easy, Mr. Client, what are you going to do about it? Well, it was quite an involved process of options review, selection, figuring out how it could be done. The paper describes it in a little bit more detail, and there have been other presentations on that, so I'm not going to dive too far into that. But nevertheless, this was a project where those three involving different disciplines had to be done in parallel to the detailed design. So, you know, product acceptance is sometimes seen as a significant issue, and if these were completely, you know, new, then yeah, that can be a more challenging process, but some of these were being imported rather than invented. So the precast elements, worth a quick mention of why they look a little bit different. So for a couple of reasons, we decided not to cast the precast elements with the bolt fixings already in their precise positions. One was because we were on a viaduct, and there was quite some concern that there would be some deflections when casting things in place. And that was because with a long viaduct deck of 100 meters and a longitudinal drainage concept, the depth of the self-compacting concrete under the precast slabs was quite deep. And therefore, the addition of weight was felt could impact the geometry quality. How significant that was in the end, it wasn't as much as feared, but nevertheless, having a separation where we actually fixed the fastenings in a final step solved that problem. There was also the question of how good the tolerances would be achieved by not just the precast manufacturer, but specifically also the S&C manufacturer, which had already been selected and was predominantly a supply for a lot of turnouts for ballasted track. And it wasn't high speed, so there was some concern that if we tried to be too precise up front, then we could have some problems in positioning. So I'm not going to say too much about elasticity. You just heard from Getzner. The same process was adopted in configuring the baseplate system, which was provided by CEng. And there you see the Unistar switch drive system, which had been used in quite a few countries before. So it was good in this case when we proposed it to Network Rail that they had already seen it, and therefore their signaling and S&C department were very happy for a project to actually propose to use it for the first time. In fact, it got used on ballasted track before this project was completed. So mentioning other people, there was a lot of people to work with on a project, there usually are, but this is just an indication of the range of them. Involved in the track, quite a few different people. Pod track, we're doing welding for us, but apart from that, not too much. POR and VCE doing the detailed design for manufacture for the precast panels themselves. And then we had, obviously, the switch drives, but a different installer. So all of these we had to work alongside. And Network Rail were involved, even though they weren't the project client, they were indeed the end client, and it's to their standards, and therefore they had to be involved in design sign-off and product acceptance. The second key issue is track-bridge interaction, and it's a pet subject of mine now. It's very interesting and not always completely intuitive, but basically bridges do their thing and track has its behavior, and actually when you add them together, they're not always 100% compatible. So it's important to understand that the track has certain levels of stress in it, and particularly in curves. There are additional effects in curves. Stresses in rails are different. So that when you superimpose on that the behavior that a bridge wants to do, which is expansion, contraction, flexure to some degree, the track system has to be able to deal with that. So if the bridge designer doesn't really comprehend the seriousness of that, then they can make a design that's actually quite difficult to put a track on. And in this case, we had to deal with some deck end rotations and some translation movements vertically, horizontally at bridge decks, which meant that we ended up with a particular arrangement which we'd actually seen in Germany already, which is again the Schwiehag BSP support point, which allows a little bit of extra movement and has some uplift resistance. And that, in the design, we proved once we'd fully interpreted the designs done by Arcadis, we were able to implement as a team with VCE doing the detailed design of the track slabs and the arrangement, fixing those to the deck underneath. Sounds simple there, but actually it took quite a process to explain the challenge and why actually it was additional work that we had to do in order to make it to actually function. So it took a few months to get through that process of realizing the change was needed and delivering it. In total, the design required over 700 panels, but over 100 different geometries. Because of the curvatures, because of the deck length limitations, because of some specific details, plus the S&C, there was quite a few different precast shapes required. So that did involve quite an effort from the design team. Here's one of the examples where we had to get involved and try to adjust, let's say, the original design. At pier number 14, it was a big pier for an emergency walkway concept, and it fitted between two transport ways underneath. One was a road. And I'm just going to step quickly through the reasoning we had to go through. So the first one was they wanted a big box full of fill. And big boxes full of fill are not that easy to compact. So their design was to sit a capping slab on top of the fill, and then to have us cast the track on top of that. And we had to explain in graphic detail, this graphic detail, why that wasn't going to work. So when the deck flexes, you have some uplift. There's going to be some settlement in the fill. That means that the track system is going to rotate a little bit. You also have a bit of traction and braking, and basically it's going to crack. It's not going to work. It wasn't going to last. So we were able to persuade them after quite a lot of persuasion, let's say, that they really should provide something a little bit different. And indeed, that is what was generated in the end. They designed a trough-shaped capping slab that actually sat on the pier and meant they didn't have the safety issues of lowering people and plant in to provide the fill. The station was also a pretty complicated area. It was done by a different design team from the structures designers, and mainly they were expert in the buildings area. And they gave a very complicated shape that we had to fit with, which had some shear keys, some waterproofing things, and it was quite heavily reinforced. And the real challenge was, how could we provide the track system into that space in a sequence that would work? So this is where the key interaction between construction planning and design really needs to work hand in hand. So this is why I mentioned collaboration. It's good to know each other really well and be able to push ideas to and fro to come up with the right solution to make it buildable. And in this case, it included development of a piece of plant which had to be bespoke because of the size of everything, which we then did use elsewhere on the project. But we actually ended up designing the concrete layer to be done in 2 stages. One actually supported the plant, and the second one then enabled everything to be delivered. Sorry, the second stage of concrete was filling in around the slabs. So we move on to installation. Planning for installation was pretty important. There was quite a complicated logistics on the site. We made use of 3D tools for that. This is how we were handed over the viaduct with stirrups designed to fit the shear keys. This was also designed by VCE. So everything was done on a 3D model to make sure things would fit, and pretty much all of them were cast in the right place. Not many changes required. The planning, everything had to be lifted. So there was a place where we could crane things up, and that was the methodology we used for delivering all the slabs, and indeed the plant, as you can see here, to the viaduct. The gantries then distributed the slabs into position, in the most part. Here in the station, you see a gantry running on the rails on that side piece, and then on the right you see the finalized condition. In some places, we could deliver the slabs by crane. At some times, we had to do the final alignment at night. The reason for that was we found the steel girders actually had an interesting behavior that the designers didn't tell anybody about, and that was because it was the steel girders, which are weathering steel, which means it's not painted. They're quite dark rust color, and they actually hogged by up to 16 millimeters in the summer daytime. So we actually had to do the final positioning and casting at nighttime. We had to install quite a lot of bracing because of tight radii. We did really have quite a lot of horizontal forces to counter when we finally got the positioning good. And we had to use a variety of methods of concrete delivery. Because the crane couldn't get along the whole way. We had some pumping, we had to use some transport, each of them designed according to need. Overall, it's a nice result. Nice smooth alignment, despite those challenges. Looks very convenient. And I think that allows me to move quickly onto installation. So, is that going to run?
Please, Barnaby, look at the time.
So we have a time-lapse video of the S&C construction, which just gives an indication of the process. So from the bare deck, we had reinforcement because the STC layer, as I mentioned earlier, is a little bit thicker than you might normally have, up to over 30 centimeters here at the ends. Then we have the shuttering, first positioning. Concreting of the precast slabs, then a final alignment phase, and everything finished with positioning and grouting of the base plates. And there's some snapshots of that process, so I'm going to fly through those. And there we have the finished S&C. So it's performing very well. So just quickly wrapping up with some conclusions. I did want to mention BIM again. VCE and ourselves worked with the 3D models, but one thing we did learn, it's not just a question of working in 3D. Implementation actually involves some other dimensions, temperature and time, because with dead load, bridge decks do actually deflect, so therefore understanding your positioning and understanding your structures is pretty important. And then finally, really, track-bridge interaction, a little bit like was mentioned for the acoustics. It's a cyclic process, really, ideally. Involve your specialists at an early stage, not just one discipline, but both. The track engineers with some knowledge need to be there when the bridges are being conceived. And final slide, the conclusion. It was opened in July 2022. The track took 4 months, 711 precast slabs, quite a lot of self-compacting concrete, a total slab track length of, route length of 1.7 kilometers, and the client is very happy. So it was a good conclusion. Thank you very much for your attention.
Thank you. Thank you of your presentation and to show us something about slab on viaduct. Thank you again. The next one, the third one, is Mr. Mehdi Maghfouri. I don't know if I pronounce well. Who tell us something about preventive measure on slab tracks. Thank you.
Good afternoon, everyone. My name is Mehdi. I'm originally Persian. I started my work in the Middle East. After a few years working in the Middle East, I moved to Malaysia and Singapore, being involved in the project in East Asia. And now in my beautiful work journey, I have a chance to be in India, in colorful India, for two projects. One project already completed, which was the semi-high-speed rail by using of the port technology, 82 kilometers semi-high-speed rail. And then the second project, which is the current one, is the first bullet train project in India, 500 kilometers between Ahmedabad and Mumbai. So I would like to discuss about the preventive measures for resilience of the slab track that we have used for or using for these two projects. I'm going to talk about the basically evaluation of the slab track system, global preference of the slab track system, cost share of the precast slab, and process of manufacturing and installation of the slab track, key factors influencing resilience of the slab tracks in different stages, such as pre-pouring, pouring, post-pouring, and installation, correlation matrix for the resilient slab track, and then last but not least, engineering recommendation for the slab tracks. All right, so here I want to basically talk about the evolution of the slab track. For the first time, the system was developed in 1960. Between 1960 to 1980, the first concept of the design in order to replace the ballasted system was introduced by Japanese and German with the focus on the stability and low maintenance by considering of the speed of about 210 kilometers per hour. Then in 1990 to 2000, system diversion happened. So different systems like a precast concrete elements and cast in situ design came into the picture with the focus on the easy construction and vibration control. Then in 2000 and 2010, rapid system integration happened. Then the slab track became the standard for high-speed rail with the focusing on the fastening technology. So some sort of new era for the fastening technology has happened that time. And then from 2010 until present time, which is the modern era of the high-speed or precast slab systems, we can see the dominance of these precast items, these precast elements for the slab, for the high-speed system. And then the focus nowadays is more into integration of the AI, as discussed yesterday, digital QC and life cycle cost optimization, with considering the speed of 350 and recently in China, more than 400, so it's being implemented. But why slab track system is, there is a preference for that. There is a global preference for this kind of system, basically, because of this precision and quality, and fast construction and reduced disruption, enhanced durability, lower life cycle maintenance, and reliability proven. I will go through each point and discuss with some examples. All right, we are always talking about precision and quality, but how much, how precise should be the slabs? Here I have a comparison, not the comparison, basically two examples of two systems, pour and Shinkansen system that we are working on. You can see, for example, under the JS slab, the length of the slab is about 5 meters, but we have the tolerance of 3 mm only. It shows how accurate it should be. And we always, again, talk about the precision, but we have to also consider how sensitive is the production of the slab tracks, how we can achieve this kind of strict, in a way, tolerance. The next item is the fast construction and installation. Here I have a scenario why we are saying that this is quite fast. Why? Because, for example, the production of one slab track, or one slab track, it takes about 20 hours, more or less. All right, so let's consider we have 100-kilometer single track. So a slab production rate could be between 50 to 100 slabs per day. It depends on the quantity of the molds. So the total production period, based on 26 days working per month, would be about 8 months. Installation rate that we are currently doing for the Shinkansen system is 200 meters per day. In this case, the total installation period would be about 4 months. Total production installation period could be about 6 months, with considering of 2 months buffer stock for the slabs. It shows that within 6 months, regardless of the grouting and some, pulling the rail or installation, rail installation and so on, the welding, we can complete the 100-kilometer single track within 6 months. So it shows how fast is the system. The slab also is durable. We are talking about the durability. We were talking about the life cycle, like 50 years, 90 years, 80 years. It was discussed again yesterday. But why we are saying that the system is durable, the slab track is durable? Because, of course, nowadays by having the, so I categorize it into the materials and the design and some tests. Coming to the materials, nowadays by having the advanced concrete technology, using of the supplementary cementitious material, we can enhance the microstructure of the concrete in order to have a durable concrete which can guarantee the life cycle of minimum 50 years. Not only that material, but also we have to do the tests. We do the static load test, dynamic load test, as well as the thermal gradient test. You can see here, we have the different options, different temperature difference on the top surface, bottom surface of the slab. We have to know if the slab under the different temperature would be durable or not, and also check the deflection. That's but shows the perfect result. That's why we say that the slab track system is basically durable and reliable. We are talking about the lower life cycle maintenance. The first thing, whenever we talk about the slab track, the first thing which comes into the picture is that, okay, slab track system is quite expensive. Or no, not quite, actually it's very expensive. Yes, that's right. According to Japanese, about 1.5 to 2 times higher than the ballasted track. But the key point is the maintenance cost. Some people say that, or some companies say that, okay, so the maintenance cost could be 0. Maybe he's right, but let's consider at least 25%. So 25% compared to the ballasted system is something significant. Meaning to say that, for example, after 10 to 12 years, again, according to the Japanese, we can have the balance between the cost and the maintenance, which is excellent. So same studies also have been done in Europe, which confirm this matter, basically. All right, we talk about the reliability of the slab track. You know, they have done so many projects. I'm not talking about Europe because I have been more into Asia side. So in China, 42,000 kilometers of the high-speed rail slab track system already been there. Already implemented, operational already, with the speed of 350, and as I told you recently, up to 420. And same goes with Japan and Taiwan. And the interesting thing is that, for example, for India, the project that I just mentioned that we are working on is the 3rd time in the world after Japan and Taiwan. So because the system was reliable, that's why in India they decided to have this kind of system to improve the, basically, the railway structures. And you can see most of the system already being influenced by Shinkansen Japan in Asia. So all the points confirming that the system is reliable, that's why the tendency is there. We were discussing that, okay, so it's good to encourage countries or people to have the slab track system. Yes, it can be, and we have to do, because it is already proven. All right, so talking about the cost share of the precast slab track. The cost of the precast slab track itself is about basically 15% of the total cost of the project, while we have the rolling stock of 15%, electrification and signaling 15%, stations, construction 20%, tunnel 35%. Again, back to the precast slab track, 15% is significant. Meaning to say that we have to be so careful when we produce the slab tracks, and we have no room to lose them or having some rejection. That's why resilience slab track come into the picture. But before I discuss about the defects on the slab tracks and preventive measures, I would like to draw your attention to the process of the manufacturing and installation. Basically, the first stage is the reinforcement cage making, which can be done parallelly with mold cleaning and preparation. Once the mold cleaning done, then the cage, fabricated cage, steel cage, can be placed inside of the mold and then followed by the concreting. Of course, before the concreting, we need to have the inspection of the reinforcement and mold again, because we don't want to face any issue later on, and then proceed with the pouring, concrete pouring. After pouring, of course, proper vibration should be in place, and then finishing of the concrete surface, and then goes with the initial curing. Initial curing could be just a normal curing, just covering the concrete surface, or could be a steam curing. Steam curing by up to about 55 degrees, especially in Europe. In order to have the faster demolding process, we need to have the steam with the temperature between 50 to 55 degrees. However, in what we are practicing under the Japanese system in India, we can go up to only 40 degrees. And the reason could be avoid any micro cracks inside of the concrete. That is the reason that Japanese are really particular. But basically, we cannot go up to very high temperature because of the delay ettringite formation, which can cause serious defects in concrete microstructure. All right, and then after the curing, initial curing, the demolding process, and then post-pouring inspection, and then the post-pouring inspection could be just a visual inspection, just to see if there is any defect or not, and then followed by the geometry inspection, and then secondary curing, if required. In Shinkansen system, basically, secondary curing is required. So we keep the slabs in the water for another 3 days to complete the curing process and the hydration process. Then the slab can be moved to the storage yard and then followed by the site delivery. And sometimes it's required to have the site storage. And then, of course, the shoulder installation before the shifting of the slabs on the viaduct, and then slab laying, and then longitudinal, vertical, and lateral slab adjustment, and last but not least, grouting. Grouting could be either SCC or cement asphalt mortar. System by system could be different. All right, so In coming 4 slides, I'm going just to discuss about what kind of defects. Actually, there are many types of defects, which shows that, again, how we have to be careful during the production process and installation to avoid all those defects. Mold cleaning, as I just mentioned, mold cleaning is one of the steps. If not the proper mold cleaning in place, the poor surface finish, buckles and edge defects might be happen. What can we do is just to remove the hardened concrete, inspect the corners, joints, and insert location, apply release oil, and clean and insert seats. Mold geometry, another item is the mold geometry. If you don't have the proper mold geometry, so the rounded edge, uneven surface, and gaps in mold joints could be happen. So we have to verify the dimension, and of course, we have to ensure the proper joint closure. Whatever here I mentioned, I mean, in different projects, we have a struggle a lot with the client, with the consultant, so that's why I'm highlighting these points. Reinforcement cage quality. This is also important. After if we don't do the proper one, so uneven cover cage, bond issues, and cage deformation could be happen. We have to place and secure the cage using the cover blocks and the rebars to be clean, dust-free, and properly fixed. Insert fixation as well. There's another item. We have a lot of problems actually with the fixations. Even in sleepers, those dowels, based on the degree that we have to fix them, sometimes the degree is not there, the inclination is not there, and then, of course, might be the precast product might be rejected. This is also very important. Most of the rejection comes from this particular point. So we have to use the jigs or clamps to fix the dowels or insert and inspect after final position before pouring. Concrete quality, you know, because this is a concrete product. So many problems also coming from the concrete. Segregation happen, bleeding on the top, and then strength or durability could be also in a weak point. So we have to have the proper batching plant system and then proper concrete transportation. It's very important for the production of the slab track, such a precise product. We have to have a fully automated system. For example, the fully automated batching plant and then traveling bucket to transfer the concrete, transport the concrete from the batching plant to the discharge point. You know, for example, in Japan, they are still using the truck mixer for the same system, because I'm in contact with my friends in Japan for the same Shinkansen project, which is in progress. They are still using those kind of traditional system, but with the low quantity of the product. But once we go to the massive production, we need to have the high level of the automation. Uniform concreting, uneven concrete pouring can be placed and can be happen and voids or honeycombs. So the concrete shall be discharged layer by layer and then do the proper vibration. The duration, everything is really important. Either the pneumatic or electric vibration, mold vibration shall be used, and then, of course, the adequate vibration frequency. Finishing also is important because we don't want to lose the tolerance that I already mentioned about. So that's why finished surface according to design tolerance must be there and avoid overworking the surface. Because we don't want to have the weak layer on the top.
Please, Mehdi, look at the time.
And then curing. Most of the defects actually coming from the curing, because if not the proper curing in place, we will have the different types of the cracks, like shrinkage cracks, plastic shrinkage cracks, and and so on. So that's why the curing also shall be controlled. Concrete maturity. If concrete is not mature enough and we start doing the demolding, again, some defect like cracks or age damage could be happen to the slabs. And here also I mentioned that, okay, so for example, proper demolding tools we have to apply, gradual and uniform release pressure. You know, if we don't use the proper demolding equipment, sure, we will have a lot of issues with the defect on the slabs. We have faced this problem. We have faced this issue. That's why proper frame shall be designed and being implemented for the demolding. And then lifting, some cracks can be happen, some defect can be happen during the lifting, and correct lifting points and anchors, and check the crane capacity before the lifting shall be carried out. The factory layout is very important because we don't want to have so much handling. The more handling, the more defect might be happen. So that's why it is strongly recommended that to have a linear factory layout, and a storage yard, of course, should be leveled and in a proper surface, ground surface. And then the transportation, some cracking, surface damage also happening during the transportation. Use a level surface, use a proper spacer, avoid the excessive stacking shall be done. And then site handling and grouting. So these items must be basically considered to avoid the defects. So I already categorized the defects. First, we have to study the root cause and do analysis. Once we know them, in case of defect happen, the first thing is to define acceptance criteria and then come up with a method statement and obtain the approval from the designer or from the client. And then based on the defect, if the defect is repairable, then we can do the repairing and then conduct the final inspection, and the slab would be ready to use. If not, then designer review must come into the picture, and then if it's okay, then we can do the repairing and then go for the, we can use that particular stuff for the sections with the lowest speed. So if not okay, then of course the slab would be rejected. That we don't want. So the last slide, just a conclusion. I would say that we have to train our production and installation team, what do you call that, regularly. So the concrete mixture must be optimized and suit the purpose for the slab track production, and high level of the automation for the concrete production and distribution shall be in place. Control curing environment, high level of the accuracy and durability of the mold. Mold is very important. If you have a complicated mold, basically the demolding would be very difficult and tough with so many defects. And then demolding criteria and equipment shall be there, minimize indoor handling of the slab track, and then handling and transport protocol shall be there, and inspect the procedures time to time. And last but not least, the defect identification and remedial action according to the approval method statement. Thank you very much.
Thank you, Mehdi. Thank you for your presentation. Thank you. And I invite the Marinella Giunta. Well, thank you. Who speaks about environmental emission analysis of slab track. So it's to you.
Thank you, Engineer Giovine, for the introduction. It's a pleasure for me to be here in this, to participate to this railway forum. It's my first time attending. I heard interesting speeches from qualified speakers, and hope I can say something interesting too. I'm truly delighted to be in such an iconic place for the history of the Italian railways. Today I will discuss the environmental aspects of the slab track system. The need of consider also the environmental aspects as well as the technical aspect as discussed during this forum arise from the need of make the track sustainable, also the railway track sustainable. Before delving into the environmental analysis, let me recall some key aspects of the slab track. Regarding the application, slab track is a suitable solution for subways, tunnel, tramways, and in general in a space-constrained environment. Key features are, in fact, the reduced structural depth, but also the better load distribution and the high geometric stability, which ensure the long-term alignment accuracy. Advantages is the extended service life. We talk about 16 years, but also about 100 years in service life, depending of the design. The lower maintenance, but also the faster installation and higher quality due to the prefabrication and modular design. There are also the drawbacks, the challenges. One of these is the higher initial construction cost, but also the high carbon footprint due to the use of the concrete, which is an emissive materials. In particular, cement, steel, but also some additives are emissive. To evaluate when we compare to track system, it's important to make a comprehensive evaluation considering the technical, economical, environmental aspects in a life cycle perspective. And among the various parameters, it's important to consider the environmental cost, which plays an important role when we compare, in example, a ballast truck and slab truck. My previous studies demonstrated that the break-even point of the total costs, not only on the construction costs, but construction and maintenance costs, but considering also the user costs, the cost of the disruption, or the environmental costs, the evaluated, assessed to the monetization of the environmental impacts. The break-even point can take several years to achieve from construction. This depends on the traffic intensity and the maintenance frequency of the ballasted truck. Reducing the environmental impact of railway infrastructure is essential to align with the European sustainability target and to the goal of decarbonizing the transportation sector. I would remember that the 25% of carbon emission in the world is produced by the transport sector. Building on this consideration, the objective of the study I'm presenting, this is a study elaborated with my research group at Mediterranea University of Reggio Calabria, is evaluated environmental performance of slab track system through the life cycle assessment methodology. The scope of the study covers all stages of the production of the slab track, so raw material extraction, transportation, and manufacturing. And the study considers cutting-edge technological alternatives such as high-performance concrete, fly ash-based mixture, recycled aggregate plastics, but also slimmer slab designs. And with the final objective of highlight a solution that can significantly reduce the environmental impact. Method applied is the life cycle assessment carried out according to the framework established in the ISO 4040 standard. A life cycle assessment encompasses 4 stages: goal and scope definition, life cycle inventory, the life cycle impact assessment, and the interpretation of the results. We made the life cycle assessment of the slab, different alternatives of slab track by means of the software OpenLCA and using the EcoInvent database for the processes. In order to estimate the life cycle impact, we applied the Recipe method, the midpoint Recipe method, and we consider 18 impact categories. We quantified 18 impact categories. Before made the environmental analysis, 2 important elements must be defined: the functional unit and the system boundary. The functional unit is the unit of reference, the reference unit for evaluate the performance of a system and for make the comparison among different alternatives. In this case, we used one slab. The life cycle system boundary implementer are the cradle to gate. So we consider only the resource extraction, the transportation, and the manufacturing side. We excluded from the study the construction, the operation, the maintenance, and the end of life, because the alternatives under the scenarios under analysis behaves at the same way in these stages of the life cycle. Regarding the examined scenarios, we consider the Ariana slab track as a reference scenario, and this because Ariana slab track is widespread in Italy. 42,000 slabs have been installed. Yesterday, engineer Gavazzeni said it. And we chose also this solution because relevant data were available to support the environmental analysis and comparison. The other scenarios were considered starting from the Arianna slab track and varying some characteristics. For instance, we considered a scenario in which 30% of aggregate by weight is from recycling, in particular from recycling of dismantled ballast. Another scenario considered the use of geopolymer concrete, in which the 20% of the clinker is replaced by fly ash. The use of high-performance concrete characterized by low water cement ratio, high content of concrete, and high-performance superplasticizers. The fiber-reinforced concrete, in which the 30% of traditional reinforcement, steel reinforcement, is replaced with steel fibers. The thin slab, a slab with reduced thick, 16 centimeter instead of 18, and the polymer modified concrete with recycled polymer. This is a scenario in which the 10% of cement is substituted by recycled SBS. And another scenario in which the same scenario, polymer modified concrete, but with virgin polymer, in order to assess the improvement of the recycling of the polymer. For all alternative detailed life cycle inventory was performed. The life cycle inventory covers all input and output associated with the raw material extraction, transportation, and production process. And from the life cycle inventory, it's possible to make the subsequent life cycle impact assessment. The impact categories quantified are reported in the slide. Let's move to the results. In this graph are reported in x-axis all the impact categories considered, and in y-axis the values, while the different colors of the bar are referred to the different alternatives under consideration. It's possible to observe that there are some impact categories referred to the terrestrial ecotoxicity, the human ecotoxicity, the mineral depletion, and the global warm potential prevails. And inside these impact categories, it's possible to observe different performance of the alternatives. In example, the polymer modified concrete with virgin polymer present the highest values, while the fiber reinforced concrete the lowest. To analyze better these results, in this graph is reported the percentage variation with respect to the Arianna slab, with respect to the reference scenario. Positive values indicate a worsening, while negative values represent an improvement with respect to the reference scenario. It's possible to observe that the polymer modified concrete with not recycled values higher than, for all the impact categories, values higher than that of the Ariane slab track, while all the other alternatives present values, lower values, and in some case, with reference to some impact categories, there's a variation, so the improvement ranges from 20 to 30%. Focusing on the global warm potential, here are reported the values of this indicator. This is one of the most important indicator in the environmental analysis in the comparison of different solutions. This is the results, and this is in this graph are reported the variations with respect to the Ariane slab track. Is confirmed the bad performance of the polymer modified concrete with not recycled polymer, and while in example the geopolymer concrete, but also the T-slab exhibit the better behavior under this standpoint. In the use of recycled aggregates as a negligible contribution to the improvement of the global warm potential. Regarding the contribution of production stages, of the 3 production stages we considered to the environmental impact categories of slab track, it's possible to observe that raw material contribute for 90% and more to the impact categories, to the values of the impact categories. This highlights the need of focus attention to the selection of the material, to the design of the materials. This aspect can contribute to improve the sustainability of the truck. The manufacturing contributes for about from 3 to 6%, while the transportation have a minor contribution from 1 to 2%. In conclusion, slab track system offer advantages in durability, maintenance, modular construction, but the carbon footprint is high, is a concern when we talk about slab track system. The life cycle assessment is a methodology that is essential to understand environmental impact across all production stages. The analysis carried out allows to assess the performance of the different alternatives, and we can see that geopolymer concrete and T-slab produce a reduction in impact of about 11%. The fiber-reinforced concrete and recycled polymer modified concrete produce significant improvements. Recycled aggregates alone have limited effect, and the virgin polymer concrete increases the impact. In conclusion, it's possible to affirm that combining innovative materials, smart design, recycling strategies, it's possible to build railway infrastructure that is not only efficient and durable, but also sustainable, meeting today's need without compromising the environment for future generations. This is the meaning of the sustainability as stated in from the United Nations Brundtland Commission. This study belongs to a wide research project carried out within the MOST, the Sustainable Mobility National Center, spoke for railways. Thank you for your attention.
Thank you for your presentation, full of interesting information. So we are a little in later, but we have time for a couple of questions, if you have.
Yes, Rick Monteban again. Barnaby, question for you. I might have missed it in the presentation, but I wasn't asleep, I promise you. What was the reason for choosing the steel girders as an interruption of the concrete bridge decks?
I believe it was just the complexity. So that was on the tight radius, and with a range of obstacles underneath, they couldn't continue. If it had been a straight line, I think it would have just been obviously the same design, which was a 50-meter deck, 2-span, 25-meter span. The steel girders were all simple spans, apart from one where they had some extra columns in the middle where it was spanning over the high-speed 1 railway tunnels. So it was the complexity and the geometry. So it was more bespoke, and therefore that's easier to do.
Thank you.
With the steel.
There are no other questions, so I say conclude this section. And there is the lunch waiting for us, and we see later at 2, if I remember well. Thank you to all the speakers and to all the audience persons.
Clock strikes upon the hour, and the sun